and welcome to the Spring 2025 virtual presentation on behalf of General Dynamics Electric Boat. The project is High Reliability Dynamically Reconfigurable Optical Networks. These are our technical directors. Pictured on the left is Michael J. Bronner, staff engineer, and pictured on the right is Joshua A. Malero, communications engineer. This is our capstone design team. My name is Kylie Pasternak. I am pictured on the right, and I am an electrical engineering major. On the far left is Alexander Gill, who is also an electrical engineering major. In the center is Austin Noon, who is a double major in computer engineering and applied mathematics. GDEB was established on February 7, 1899. Its mission was to revolutionize naval warfare. Key accomplishments include creating the Holland in 1900, which was the first commissioned U.S. Navy submarine, the USS Nautilus in 1958, which was the first nuclear-powered submarine, and the Virginia-class submarine program, which was the first major warship completely designed in a virtual environment. They are currently working on the Columbia-class submarine program, which will replace Ohio-class ballistic missile submarines. Our project motivation is to incorporate next-generation add-drop networking technology into a fiber optic network. We're looking to develop a tactical middleware, which is the interface between system providers and vehicle networks. This will enable a flexible, robust, and highly reliable network. Such a network will reduce platform integration costs and enable the integration of new technology into current networking infrastructures. The anticipated best outcome was achieved. Our key accomplishments were technology investigation of several trade space areas, 3 types of media converter simulations, successful design of a full mesh star hybrid network topology, a ROADM Simulink model, transport layer 4 simulation, and the successful integration of models and simulations. Team GDEB designed and modeled a simulation prototype of a dynamically reconfigurable data network which implements next-generation add-drop technology. There is an economic benefit to introducing OADMs. Expanding fiber optics can be costly. By introducing OADMs, these costs can be cut. Rather than implementing new fiber, implement OADMs into the network to increase its capacity and range. OADMs are reliable. In turn, they can cut costs that would be spent on downtime. Pictured on the right is our ROADM Simulink model. This block diagram represents the physical network layer 1. The left side of the block diagram, outside the circle, is related to my technical contributions, which is media conversion. The right side of the block diagram, inside the circle, is related to the network topology, ROADM simulation, and network transport layer 4 simulation. I designed 3 media converter simulations to model the receipt of input signals from existing cabled infrastructure. The 3 input signals are HDMI data, specifically a 1 megabyte video, copper data as in a 126 byte Ethernet data packet, and serial data which is represented in an 8-bit binary. Each of the simulations take in the signal and mimic the media conversion process by encoding or compressing the signal, adding noise to represent transmission, and decoding or decompressing the signal. The results of each of the 3 media converter simulations are pictured. On the left are the serial to fiber simulation results, which input 8-bit binary data. The plots from top to bottom, left to right, represent the original serial data, the encoded data using non-return to 0 encoding, the transmitted signal with added Gaussian noise, and the received and decoded serial packets. The signal was transmitted successfully with a bit error rate of 0, so no bits were lost, and the signal-to-noise ratio of 17.8 decibels, which indicates that the signal was transmitted with some degradation. In the center is the HDMI to fiber simulation, which inputs a 1 megabyte video signal. The plots from top to bottom, left to right, represent the original video, the compressed video, the decomposed and noisy video frames. The video signal was transmitted successfully, and the peak signal-to-noise ratio of 41.6 decibels indicates that the quality of the signal is relatively good. Audio was lost in the process due to the method used, but could be retained in future versions of the code. On the right are the copper to fiber simulation results, which inputs a 126-bit binary ether data packet. The plots from top to bottom, left to right, represent the original Ethernet packet data, the encoded data using non-return to zero encoding, the transmitted signal with added Gaussian noise, and the received and decoded data packets. The signal was transmitted successfully with a bit error rate of 0, so no bits were lost, and the signal to noise ratio of 26.1 decibels indicates that the transmitted signal was barely degraded. The next capstone designer to speak on our technical accomplishments is Austin Noon.
Thank you, Kylie. So, my first technical accomplishment of this semester was modeling a ROTM node in Simulink. So, just to take you through the model here, starting on the very left, I have a WDM modeled input, which is wavelength division multiplexing. This is done by using 3 wave generator blocks, generating sine waves at different frequencies, specifically 5 gigahertz, 2.4 gigahertz, and 30 megahertz. These are then sent to zero-order hold blocks, which are used to sample the signals at very high rates, and then the output of these blocks is sent to a multiplexer to multiplex them into the same time domain. Moving on, after that multiplexer, there are 2 scope blocks, which are used to view the multiplex signal. Each one gives a different view, and then these multiplex signals are then demultiplexed and sent as input to a WSS subsystem block, which is a wavelength selective switch. Inside this block, I have 3 switch blocks set up to take in each signal, as well as take in control inputs. So the control inputs are based off of the WSS control function block. This takes 3 variables as input: the current node, the simulation clock, and the simulation stop time. And this function uses a predetermined routing matrix built in a different MATLAB file, and it loads those pre-computed routing decisions and then loads it into the WSS over the course of the simulation to make the routing decisions happen in real time. So each switch block contains a threshold value, which I set to 0.5, and that threshold value is compared against the control input value. It's either going to be 1 or 0 for high or low, and if it is a 0, the signal is blocked and it is sent to the drop port. And if the signal is passed, the control value has a value of 1, and it's passed through the WSS and further down the data stream. So for the drop port, like I said, when the value is 0, the signals are sent to the drop port, and they are then sent to terminator blocks, which kind of just kill the signal. And then when the value dynamically changes over time, it is reevaluated at the control function and then passed through the WSS. So after it's passed through the WSS, the signals get multiplexed back together to continue down the data path, and you can see that happening at MUX2 out 1, that scope. And then from this point, it will be multiplexed with input from the add port. So the add port runs off of 2 MATLAB function blocks, the add controller function block and the ran demand function block. So ran demand is just a randomizer function that spits out a number, either 0 or 1, that represents the network demand variable. So 1 would represent high network demand and 0 would represent low network demand. And this variable can be visualized at the demand val scope next to the add controller function block. So this function takes in the network demand variable, and then it shoots out 3 control signals based on the value of the variable, whether it's a 1 or a 0. So if it's a 1, new signals will be added into the data path, and if it's 0, the signals will be withheld from entering the data path. And then for the other three inputs to the add port subsystem, I have another WDM input system set up with the same signals. It's the exact same setup there for that input. And then inside the add port subsystem, it's very, very similar logic to the wavelength selective switch. So there are three switches, three inputs for the waves or the frequencies, and then three inputs for control signals. The switch blocks are set up the same way. The threshold is set to 0.5, and it's compared to the control signal input. And if it's 1, then those frequencies are passed through, they're multiplexed together, and then they're multiplexed into the existing data path already. And if it's 0, they're withheld from entering the data path at all. So lastly, the combined data flow can be seen at mux2 out2 or mux2 out on either one of those scopes. And then the last stop for the data path, you can go to the optical channel monitor, which takes the average power of the signal over time. Or, well, I should say, and it also goes to the optical amplifier, which amplifies the signal. I think its amplitude is set to 1 normally, and it amplifies it up to 3. So it amplifies the signals to make up for any signal loss or any other impairments like that. So this is some of the output from the simulation in Simulink. On the left, there's a figure. It's the data flow after the add port. So in there, you can see the three original signals are represented by yellow, blue, and orange. So you can see the dynamic nature of the simulation in effect here. You can see the orange signal it switches to a blocked signal at about 0.2 nanoseconds, and then it turns back on at about 5 nanoseconds. Same thing with the blue. The signal is blocked at about 0.2 seconds, and then it comes back on at about 1.7 seconds, and then it's blocked again at about 3.4 nanoseconds. And then you can also see the yellow frequency. It's also it's blocked to begin with, actually, and then it turns on at about 0.2, gets blocked again at about 1.7, and then it comes back on at about 3.4 and continues on. So the additional signals from the add port would be represented by the green, purple, and teal lines, which are labeled subsystem 1, subsystem 2, and subsystem 3. So in this simulation, the network demand variable was randomized to 0, so that's why you see a flat line for the teal at 0, and then the green and purple are also plotted at 0. You just can't see them. Then on the right, you can see the output of the optical channel monitor. So this plots the power level of the signals over time. There's a lot of noise, but you can see that it takes the shape of what the combined signal would look like, and it's just plotted over time. My next technical accomplishment was the MATLAB topology simulation. So in this, I conducted a simulation in MATLAB to see how data flow would behave while flowing through our network. So on the right, you can see a picture of what the network would look like. You have 2 star subnets on each end, and those are connected to each other, as well as being connected through a full mesh network right in the middle. There's a total of 30 nodes in this, and I randomized the source node and the destination node in each time step. And then you can see the data path being taken is symbolized by the red line connecting one node to the other node. And then a couple other quick things about the simulation. The way I actually constructed the topology was by using an adjacency matrix. So for each subnet, I went through and I plugged in either 1s or 0s to represent the neighbors of each node. So for example, node 11, it would have a 1 at 16, 18, 19, 17, 20, 12, 14, 13, and 15, because those are all direct connections. Also, for the routing, I used Dijkstra's algorithm to compute the shortest path from start node to end node. And then in the simulation, I also tracked end-to-end latency as well as bit error rate, and those are shown on the next slide. And then what I did with the simulation later on was I integrated results from one of Kylie's simulations, and I tested it by injecting that data into the simulation to see how some real data would flow through the network. So this is output from the simulation I just showed you. So on the left is bit error rate across the path during step 5. So at the bottom is the hop index, which is how many hops are taken in between start to end, and then the accumulated bit error rate is plotted as well. It's relatively low here, which is good. And then on the right is signal latency over time. The latency variable is completely randomized in this simulation as well. It's also measured in nanoseconds, so you can see that the end-to-end latency over time is throughout the course of the entire simulation. You can see the time steps on the x-axis, and then latency is plotted on the y. And now for the integrated simulation results, I used the output from Kylie's NRZ encoded serial data simulation, and I used that as the injection of data into the network. So hers was NRZ encoded. On the right, you can see that the original signal is the red line, and it goes from a value of 1 to -1, which is NRZ encoding, and then the received signal is just binary, so it's ones and zeros only. This also used a random source and a random destination node pairing. And then on the right is the original signal versus the received signal at the destination plotted. So you can see that there is one error at the 6th bit, at the 7th bit of the received string. And then real quick, this is just, again, bit error rate over time and the signal latency over time. Bit error rate is on the left, and signal latency is on the right. And next up is Alex. He's going to talk about his technical accomplishments as well as closing out the presentation.